Hello everyone, my name is Gabriel Schöpfer. I'm in the group of Milan Ončak at the Institute of Ion Physics and Applied Physics. And today I want to talk to you about the doubly charged argon dimer and the question if this is stable. So argon is a noble gas, as you might know. So this means that if you have a lot of argon atoms, they don't want to make bonds and create molecules, they just want to stay alone. So basically they're very happy alone, they're inert, they don't want to react, they don't want to make bonds. And yes, so now, but we're talking about a doubly charged argon dimer. So the question is now, we're adding a charge to all of these argon atoms. So we don't have neutral argon atoms anymore, but positively charged argon atoms, so argon ions. And now the question is, if we bring two of these together, will they make a bond? Well, intuitively, one probably would think, well, if the neutral argon atom already don't make a bond, why should the positively charged argon atoms make a bond? I mean, they already don't want to make a bond when they're neutral, and now we even charge them, so they actually want to repel each other. So yeah, why should they make a bond? However, in the experimental group of Paul Scheier, they actually measured the doubly charged argon dimer. So this is a strong indicator that it actually is strong, that it is a stable molecule. And yes, so my goal was to confirm that the argon dimer is a stable molecule through quantum chemical calculations. And today I wanna take you to a journey to the argon dimer, to the doubly charged argon dimer, in order to show you why it might be actually stable or why they could measure it. Alright, so let's start with the basics. Argon is a noble gas. The noble gases are here on the right hand side of the periodic table. Argon is here exactly. So as all of the noble gases, argon is very inert and it doesn't want to react. But so why is it actually so stable, and why are all noble gases so stable? So this is because of the distribution of the electrons in the orbitals. So basically all noble gases have only completely filled subshells. So in the case of argon, this means that the 1s subshell, the 2s subshell, the 2p subshell, 3s, 3p subshell, they're all completely filled, and all of the higher lying subshells like 3d, 4s and so on, they're completely empty. And this is why they're so stable. So basically, filled subshells, this is what atoms want. They like this. And the argon actually has everything that it wants, so it doesn't want to react with anyone, it's happy alone, and that's why argon atoms are so stable, and you cannot build or you cannot really build, like maybe at very low temperatures, but usually argon atoms don't want to make argon molecules, they prefer to be alone. Yes, so now, as I said, we're having an argon dimer. So this means that we're having two argon atoms. So in general, dimer is just a molecule consisting of two parts. In this case, it's a molecule consisting of two argon atoms. And our argon dimer is doubly charged. So this means on each of the two argon atoms, there is one positive charge, as you can see indicated here. And now the question is if this is stable or not. So what do we actually mean by stable? So possibility 1, unstable, would mean if we bring these two argon plus ions together, they repel each other. So they don't want to stay together, they prefer to be alone. So this would look like that. The second option is that they're stable. So if we bring two argon atoms, like two positively charged argon atoms close to each other, they actually move further together and make a bond. So yes, as I said in the experiment, it was measured to be stable. But so let's try to approach this question first from a very basic idea. So let's assume the two argon atoms are really just two positive point charges. And this is a very simple model, but it's probably the best simple model that you can make. But it's of course not a good model. But if we say these are just 2 point charges, well, what will happen? Exactly, they will just move away from each other. So this strongly indicates that there is some attractive force in the argon 2 plus dimer in order to stabilize the argon dimer molecule. And in order to understand this, we actually need to look at the orbital scheme in argon. So electrons are fermions, right? So every state can only be occupied by 1 electron. So this means that in each of the orbitals, so this is an orbital, this is an orbital, this is an orbital, and so on, in every orbital there can only be 2 electrons. One of the electrons will spin up and the other one will spin down. And electrons always prefer to be in the energetically lowest lying orbitals. So basically you fill up the orbitals from below, so you start with 1s, then 2s to p, and so on, until all electrons are like live in some orbital. So now if we go to the argon plus ion, what does this mean? So we need to remove one of the electrons, right? So which electron do we remove? Well, yes, of course, we remove the electron that is in the highest lying orbital. So we remove one of the electrons in the 3p orbital. And now if you look at this, you can actually already see that in argon plus we don't have this completely filled subshells anymore. We have here one of the subshells that is only partly filled. And this is the reason why argon plus is actually not a noble gas anymore. Only argon is a noble gas, but not argon plus. And this is the reason why argon plus can make bonds. And this is the reason why we eventually actually have a stable argon 2 plus molecule. So to understand now the bonding in the argon plus dimer, we have to look at the orbitals. And so as I said, the orbitals are the place where the electrons live. And for example, the 3s orbital of argon plus looks like this. So it's spherically symmetric. And this now means that with a probability of 95%, the electron is within this sphere. For example, the 3p orbital in argon is a little bit higher in energy. It has a different shape. So, and this now means that with a probability of 95%, the electron is either here or here. But it's never in between. And this pink thing here is just the nucleus. And now, if we add a second argon plus ion, what will happen? Well, they will make molecular orbitals. So basically, if the atom is alone, there will be atomic orbitals, and the electrons will sit in these atomic orbitals. However, if you add another atom or ion, then the atoms will merge and also the orbitals will merge, so the atomic orbitals will turn into molecular orbitals, and then the electrons will live in these molecular orbitals and not in the atomic orbitals anymore. However, this only happens if it's energetically favorable, so only if the resulting energy of the molecule is lower than the energy of the 2 single atoms. So let's look now at the resulting molecular orbitals. So in the case of the atomic 3s orbitals, so we have here an atomic 3s orbital and here an atomic 3s orbital, and they will make together 2 molecular orbitals, and one of them is bonding, the other one is anti-bonding, and in this molecular orbital there are 2 electrons, and in this molecular orbital there are also 2 electrons. In the case of the 3p orbitals, like this argon plus ion contributes 3 atomic orbitals, this argon plus ion contributes 3 atomic orbitals. So in total we have 6 atomic orbitals, and they will make 6 molecular orbitals. So in total we have then 6 molecular orbitals. The energy actually then splits of these molecular orbitals, so they do not have all of the same energy anymore, but actually some of them are then lower in energy, some of them are higher in energy. And also like we have in total 5 plus 5, so we have 10 electrons that we can distribute over the 6 molecular orbitals, so one of them will remain empty. Alright, so all in all we actually now have 6 electrons in bonding orbitals. So these are all the orbitals that are lower in energy than the original atomic orbitals, and they stabilize the molecule. On the other hand, we also have here 3 anti-bonding orbitals. They are higher in energy than the original atomic orbitals, but only 4 electrons are in these anti-bonding orbitals. So in total, we have more electrons in bonding than in anti-bonding orbitals. So overall, we have a stabilization of the molecule. And we can also look at this stability from a different perspective, which is the potential energy surface. So potential energy surface gives the energy of the molecule as a function of the distance of the 2 nuclei. So, and this, for example, means now that if the 2 nuclei are very close to each other, the energy is very high, so this is very bad. The molecule doesn't like it, and this is because of Pauli exclusion principle, because you basically force the electrons very close, like basically force them in the same orbitals. But if you have some nice distance between them, it's very, like the molecule likes it, and it wants to be in this distance. And then if you further, like, move them further away from each other, it's again not so good. So basically there is some optimal bond length between the nuclei, and this gives a stable molecule. Of course, we still have the Coulomb repulsion, because we do not just have two atoms that are neutral, but we have, like, there are charges on the argon atoms, right? So basically we have 2 effects that play a role. We have here this attractive covalent bond and this repulsive Coulomb interaction. And the question is now, well, what's winning basically? And in order to answer this question, in order to find out what's the more important thing here, we just need to make quantum chemical calculations. So it could either be that the Coulomb repulsion is so strong that we cannot have a stable minimum, or the covalent bond is so strong that we actually have some small local minimum where then the molecule can live for some time. So as I said, I did quantum chemical calculations, and these are the results. So how should we now understand this? So these are the states in the argon 2+ molecule. So what is a state actually? So a state is, for example, this. So this is a distribution of the electrons over the orbitals, and this is actually the ground state, because this is the state that is the best one for the molecule. Like, the electrons prefer to sit in the lowest lying orbitals, so this is how the ground state looks like. However, it's also possible that one of the electrons, or also many of the electrons, are excited into higher lying orbitals, and this is then an excited state. And so here in the diagram on the left, so this here is the ground state, and all of these states here, these represent higher lying states. And now if you want to calculate the ground state, for example, in this region, then it's totally fine to do a simple quantum chemical calculation, because the higher lying states are very far away from the ground state, and then this is fine. However, if you want to describe this region here, then you will get into troubles if you use a simple quantum chemical method. The reason is because here you have a lot of states that are very close to each other, and even if you're only interested in the ground state, you have to basically, in your calculation, you have to describe all of the states at the same time. Otherwise you will get problems in your calculation. And yes, so to do that I used like advanced method. It's called multi-reference configuration interaction method. And the point is, if we now do this calculation and then only plot the ground state, so we at every point we only plot the state that has the lowest energy, we will actually get this graph here. So here basically this graph represents only this part of the plot on the left, and from this you can clearly see that there is a local minimum in the argon 2+ dimer. So now we can finally answer this question. How does it look like? What's winning? Is the covalent bond the winning factor, or is it the Coulomb repulsion well, yes, the covalent bond is strong enough in order to stabilize the molecule here at this distance of 2 angstrom. Like an angstrom is 10 to the minus 10 meters. So yes, this is an agreement with the experiment. And so to just show you here quickly how this looks like in practice, I show you like the input file of the quantum chemical calculation. So you can see here the definition of the atom. So we have here 2 argon atoms. Here you need to define the basis. Here you need to say which orbitals you want to take into account. And here you need to say which states you're calculating. And this is basically the difficulty of the whole method, because it's not clear at all which orbitals, which states you want to calculate. It's also not clear which basis you should use. So this is what's making the calculation difficult. So to summarize, we can say argon 2,2+ has a metastable local minimum. So it has some local minimum that is here. Of course, at some point, the Coulomb repulsion will win, and the covalent bond doesn't matter anymore. They will just move away from each other. But there is some small minimum here in which the molecule can live, and this has been indicated both from the experiment and from the calculations. So yes, so this is quite good evidence. So this means if we have the 2 argon atoms here positively charged, they will move together. So thanks a lot for your attention. If you're interested, of course, you can also read up the whole article, not only about argon, but also about other heavy noble gases, and not only about dimers, but also about trimers. And so many thanks to my supervisor Milan Onchak, to Stefan Bergmeister for the measurements, and to the Austrian Academy of Sciences for the funding. And of course, thank you for listening.